Hey, welcome back to ECE 382. Today we're going to Module 8, Interfacing Input and Output. This lecture is going to have two parts. The first part's going to really go over an assembly review, so kind of some of the things that I see you guys struggling with the first couple labs. And then the second part is going to be a little bit of review of general purpose input-output, setting, clearing bits, how do you deal with outputs and inputs and all that stuff. And this will really set you up for the lab for Module 8, which will be actually interfacing hardware push buttons and LEDs so that we can create a window alarm system. So we will be using assembly code again for a portion of that lab, so I wanted to review some of that and then kind of go over the input-output again. So I saw a lot of confusion in regards to memory. And I want to point out that there's a few different main types of memory. The first being, your normal RAM and ROM memory, right? So, and if we're talking assembly, remember this is the .text section is your ROM, where code and local variables are stored. So that's ROM. Then your RAM is your .data section, and that's more of your memory. So things that we're going to store and want to be able to access between programs potentially, and global variables. So we use both of those in the assembly labs at the beginning, and I know there's a lot of confusion of which ones we were using. Typically your local variables are used to help point to addresses in memory. That allows us to have that more static global variables that's sitting there in memory. So that's your RAM and ROM. I/O ports, which we'll talk about those later, and then your PPB, don't worry about those. We'll talk about that. That's a mapping for input and output. We'll talk about that a little bit later. All right, so that's your RAM and ROM. Then you have your registers. So your registers are located within the CPU, so within the Cortex-M processor, and these are very volatile. So this is super volatile memory. So you can't, on a reboot, everything's going to go and get erased. And you only really use that for kind of when you want to process, do something on like a add or subtract, or you want to shift bits. That's where we use our registers. We bring in things from memory, put it in a register. We use some kind of assembly instruction on it, and then we put it back in memory, and then we'll save that for later. So that's the main reason for registers. Registers is where we, most of our assembly instructions will work on registers. And so we have what we call general purpose registers, which these are those R0 through R12. We know R0 is our first input to a function. It's also the return value from a function. R1, R2, R3 are also inputs to a function. And then within that function, we're allowed to change those, no issues. R4 through R11, we have to push and pop off the stack. That allows us to just make sure that that memory is, if we call a function, when we return from that function, we know that R4 through R11 is the same as what we thought it was before. And so again, this is what assembly instructions. Okay. Instructions operate on registers. And then the last kind of piece of memory is the stack. And the thing with the stack, that's again very temporary, that's within the processor as well. and we're using that to push information on. So then we can, so registers, we push and pop registers. And we do that so that we can maintain that the values on those registers and then have those after a function call. And again, local variables, we can use that to push local variables on the stack before we call a function call. And then when that function call returns, then we pop them off the stack, and we still have those local variables, but the different functions do not have access to those. And so we saw that quite a bit in our first lab with assembly. You pushed, say, R3 through R4, and then maybe the link register. And we do sometimes the link register because if you were in a function already and we're about to go into another function, that initial link register is storing our return address for our first function. So if we go into another function, which we do our branch and link command, then that's going to overwrite the link register. So we need to push that onto the stack, and then when we return from that next function, we can pop it off. We can pop it back to the link register, or another method to do it is popping it straight to the program counter, which then that program counter, which is it's one of our special registers right here. That program counter is pointing to the next instruction that should be ran. So if we pop the link register, which was storing the return address, into the program counter, that means the program counter is just going to go straight to that link address. And that is the exact same thing if we did bxlr, which is a branch indirect. What's going to happen is the link register is going to get stored into the program counter, and we're going to go to that return address. Same. So these two are very similar, but this is typically what we'll do if we're in a sub function or something along those lines. So before we get too far, I just want to step back to the registers. So I forgot to talk about the special registers. So program status register we'll see this later. That's going to hold some of the information on if we do a subtraction or a compare. That's where we're going to hold our zero flag, our overflow flag, our carryout, all of those different flags. So those are our program status registers. Program counter, like I said, that's your PC. That's pointing to your next instruction to run. Your link register is going to point to your return address, and then the stack pointer, pretty self-explanatory, but that's going to point to the location on the stack. And so that allows us. And we have to make sure the stack is balanced. What that means is if I push R3, R4, and LR onto the stack, then I need to pop 3 things. They don't have to go straight back into the exact same registers. Typically we do push and pop back into the R registers, but like we saw, we could push LR and then pop it into program counter. It doesn't matter as long as we balance the stack. That means we push the same, or we pop the same number that we had pushed. The steps of what's going on in this push command. So we're going to decrement the stack pointer. Stack builds up or backwards in memory here. So we decrement the stack pointer store. And if we're popping, then we're going to read it the stack pointer and then increment the stack pointer. All right, let's talk about load. So we saw this in class with that assembly lab, but there's 4 different types of loading memory. So okay, so this first one is just indexed So basically R0 is going to equal the value pointed to by R1, right? So this is where we can take our, key 1 adder, and that's going to be pointing to, our key 1, and we can load R1, our key 1 adder, and so now R1 holds the address of key 1, and then when I take and do load R0, R1, I'm getting the actual key 1. So that's going to be basically the contents of key 1. All right, so that is just indexed memory access. All right, this next one is immediate offset. So what that means is basically R0 equals the word pointed by R1 plus 4, and then R1's unchanged. This is immediate offset. Okay, this one is the next one, then it's pre-indexed, which means basically first we do R1 equals R1 plus 4, and then R0 equals word pointed to by R1. And post-indexed, this is what we used in the lab, is basically the idea that we first R0 equals word pointed to by R1. Then we do R1 plus 4. And we can always do load byte, and that's what we did in the lab as well, to get 1 byte at a time. So these three different, so we just have load immediate offset. Well, this one's not load immediate, since it's not a load immediate value. It is just a straight load. This one's load with immediate offset. This one's load with pre-indexed immediate offset, and this one's load with post-indexed immediate offset. And hopefully that clears that up a little bit. I know there's a bit of confusion from that. All right, Code Composer assembly directives. So not a whole lot additional I wanted to add on this, but I did want to put it in there. We will be using this .word some more. It allows us to store 32 bits of memory, so it's really convenient to store a memory address since it's 32. So we have that address, we can store it into some kind of variable. Alright, so conditionals and program status register. So we mentioned the program status registers. Here they are. The ones that are really important are the ones here, specifically n equals negative, flag, z equals 0, So of course, if we want to check if something's equal, so we do a compare, and a compare takes two registers and subtracts them. And if they're equal, the 0 flag would be a 1 because there's a 0 result, and then we know they're equal. Carry, C is carry, and then V is overflow. We don't use Q too often in this course, but those are the four primary ones. And then we can use this table to determine, okay, greater than, we have at the same time Z equals 0, so they're not equal, and the negative is equal to overflow. So if it's a negative number and there's overflow, or a negative result and there's overflow, then we know the greater than condition is true. So I talked about it before, but there's other instructions that will set these flags for us. It's really nice. So we don't have to necessarily do a compare right before. We could do an add, subtract, or multiply. And there's a divide as well. And then basically what we're going to do then is after we do one of those four commands, we can add a branch equal or a branch less than, whatever we would like. And it's going to branch if that condition is true. All right, functions. So remember, to get into a function, you typically do a branch and link to some kind of label. Branch. The branch with link sets your link register to our return address, and then branch indirect, so we're branching to our link address, is used to return from function. It's nice because, like I said before, we can just, instead of branching to the link register, we can just store or pop the link register into the PC counter. That's another way for us to return from a function. So remember, in a function, the return value is in R0. Inputs are in R0 through R3. Can change freely, but we have to push and pop the registers that we use. We don't want to just push them all between R4 and 11. And these are conventions, guides, pretty much, that we use in ARM assembly coding, so that if one person's writing one function, someone else is writing another function, we have these conventions that we know exist. Yes, it would work without pushing and popping R4 through R11, as long as you didn't use R4 and R11. But if you are not the only programmer, it's very hard to, it's impossible to enforce that. So we have these enforceable rules so that we can collaborate and work with other people. You can use conditionals to branch to a function as well. So you can use, branch, link, if it's equal, or anything along those lines. All right, logical operations. So these are logical operations. We talked about these a little bit during that first assembly lectures, but I just want to go over them a little bit more. So in the lab, you're going to be using assembly to read and write to different inputs and outputs. So say, for example, we have the address. Let's say right now, pin 50 input, which each pin has registers, and each of those registers are stored in the address. So say we want to set this address equal to R0. All right, so that's the input. So that's basically reading in a value. I can select a specific pin. So let's say port 5 is input address. All right. And so this, remember, this is port 5. This is a register. Think of it as not so much as a register, but think of it more as like a memory address that port 5 has access to. And so whenever something comes onto the input, it's stored at the memory address that corresponds with port 5 input. We can store that address into R0 using, load. But that's not kind of the point of this section. We're going to look at once we have that address into the contents of that input, how do we select a specific bit? So if I wanted to select pin port 50, I could take all the information on R0 and AND it with the immediate value 0x01. So that's going to get the value of a switch connected to port 50 if port 5's input was already in R0. And so AND, remember, is select or mask. OR is to set a bit. And by set a bit, I mean turn on. I mean set to 1. So both of those, you have to start thinking about this bit logic in all of these terms. Set, on, 1. All right, exclusive OR is to toggle. So we can think about that. If it was a 1, then it's going to be a 0. If it's a 0, it's going to be a 1. And the BIC command allows us to clear. And that's one I don't think we talked about before, but that is literally bit clear command. It's really nice. Instead of having to do something along the lines of ANDing with a 0 and only selecting the certain bits, we can use the BIC command to clear a specific bit. All right, so let's look at an example of the OR. So OR R0, R0 with, say, the immediate 0x10. That's going to turn on, and let's say this is connected to an output now, connected to port 54. If that was connected, if R0 held the memory address of 5.4. But then we'd have to store that back into memory, but that allows us to take and turn on something. Exclusive OR, and we'll see examples of these in action here in a minute, but these are just more general examples. Toggle the LED connected to pin 54 and clear BIC R0, R0. That's going to turn off the LED. Turn off, set to 0, clear, all the same word. All right, in the next video, we'll see these in action. We'll see how this relates to all the input-output ports. And we'll kind of look at and refresh our memory of the processes to read and write from memory.